Greetings, folks. So today we want to talk about how we can rewrite something given in polar coordinates and just take that point, write it in rectangular coordinates. Again, the reason this should be possible in the first place is because, like we said in the last video, these 2 points are, or any one point that's plotted can be written in either way. Again, it's just a matter of which way you are using it, that you would prefer one way or the other. Okay, but if I give it to you in one way, you should be able to write it the other and vice versa. So in this video, we're going to talk going from polar to rectangular, and in a later video, we'll do the opposite. All right. So I'm just going to draw a quick little point here. So let's draw some axes here. I was all really messy. Sorry about that. And let's pretend that for this point, I went out, and I'm giving to you polarly. I went out, let's say, right here, we'll say that that is pi over 3, about 60 degrees. And let's say we're going to go out right here. Let's say that r equals 5 units, we'll say. Equals r. So again, this is our theta, and that's our r. And therefore, this point has polar coordinates 5 comma pi over 3. Okay. The nice thing about this is that given what we know about trig, you'll be able to handle this. Remember, so let me rewrite this real quick. And we're going to write our rectangular coordinates in, we'll say, red. Okay. So the question that we have now is, this is again r theta. I'll write that in purple. This is r and theta. What we want is that same point now. Oops, sorry, I said red. That same point given in x comma y. But now that we have it on graph paper, you know, we've taken off the polar glasses. We have it on rectangular graph paper. We know how to do this, or at least we know how to count it. We would know how to get from the origin to that point. You would simply go over some amount x horizontally, and then from there you would go straight up. The key here is to remember that that is straight up, and therefore that's a right angle. You got a right triangle, folks, and therefore we know all about right triangles. We can use trig to totally answer this question, no problem at all. Alrighty, so we just need to remember our trig functions, remember? So let's see. Cosine of, let's say, theta is equal to adjacent over hypotenuse, and then sine of theta is equal to, I don't know why I said y. My brain froze. Opposite over hypotenuse. Opposite over hypotenuse. And then if we so needed to, tangent is opposite over adjacent. Okay, now if the way we wrote out this triangle, well, our hypotenuse is length r, so it's, or 5 in this case. So our hypotenuse is always going to be over 5. The opposite and the adjacent, so remember, this is our angle theta down here from the origin, again, starting from the positive x-axis up to that ray. And so our cosine, let me shrink the video here, I apologize, I'm a little too big. Sorry about that, you have to stare at me. In here, our adjacent side, the side adjacent to the angle is x. So we have x there, and our opposite side is y. Okay, here's a nice thing. We actually know what theta is, and therefore we can calculate cosine or sine of it. Since this is one of those angles where we know exactly its value, we can get it pretty nicely. If you didn't, then you would have to resort to a calculator. But so we have cosine of pi over 3 is equal to x times 5. And likewise, sine of pi over 3, I always like to put parentheses here, is equal to y over 5. And therefore, x is equal to 5 cosine, and y is equal to 5 sine. Boom, you're done. Let's actually evaluate this, because let's leave no stone unturned. We have cosine of pi over 3, remember that, 60 degrees, so it's a 30, 60, 90. And so the short side of a 30, 60, 90 is always half the hypotenuse. So it's 1/2 times 1/2 equals x, so that's going to be 5 halves, or 2.5. And sine, so the long leg of 30, 60, 90 is always root 3 over 2 times the hypotenuse. So it's going to be 5 times root 3 over 2 equal to y. And so y is equal to 5 root 3 over 2. And so that's what the coordinates at that point are. This point in polar coordinates is the same thing as 5 halves, comma 5 root 3 over 2 in rectangular coordinates. Okay, so you could either go, again, starting from the origin, swing out pi over 3, walk out 5, or you could go right, you go off to the right 5 halves, go straight up 5 root 3 over 2. We could generalize this process as you might be able to imagine. So if we were to do that, well, let's write this right here. Again, I will do polar in purple. Oh, I didn't even think of that alliteration until right now. So if you have some point here, it's right here. So you have r, you have theta here. In rectangular, so that same point, again, same point. Usually we'll say we could write the point P represented with, r comma theta. We could also write it and read in xy terms, the point P defined with xy would be simply, again, x and y, where we can say that x is equal to r cosine theta, and y is equal to r sine of theta. And that's pretty much it. So if you have any point in polar coordinates, you can write it like so in rectangular coordinates. Now, I would challenge you, before you even bother going to the next video, take a second and use this same kind of drawing, the same illustration now, and think about, if I gave you the rectangular coordinates, how could you get the polar coordinates? So again, that would be, you know how far left and up you went, or horizontally, vertically you went, and you would want to figure out how far out did you go total, and what angle did you leave the x-axis at. I'll leave that to you for now, and in the next video we'll go over that. Thanks for watching, folks. See you later.